Yes, today's lesson is going to begin with density. Yes, density, like what you did in, I'm assuming it's earth science that we did density. So density, if you remember from earth science, is mass divided by volume, okay? So mass is kind of like a measurement of weight. So that's going to be like grams, pounds. Here, typically we measure mass in grams. And then volume is going to be whatever your cubic units are. They could be centimeters cubed, they could be feet cubed, whatever it may be, okay? The other type of density we're going to look at is population density, okay? So population density is some population size. Okay, so it could be people but it could be bacteria, it could be whatever the problem is about, but it's some population size over the area that population is in. So again, notice it's just an area, so now we're talking about units cubed. So this could be under miles cubed, squared, miles squared, feet squared could be for that area, okay? So if we look on the PDF page 30 in the packet, that's at the bottom of the page is where these questions begin. Okay, so the first few are fairly straightforward, just using the formula. Okay, so this one, number one, you're given the density, okay? You're given the volume and you're asked for the mass, okay? So again, density equals mass divided by volume, okay? If you fill in what you have the density, you're looking for the mass, you could put an X in there, and you have the volume, okay? So this is just gonna be a quick little cross multiply here, and you're gonna get the mass to be 300. Now, the units of that, how do you know what the units of that is? Well, if you look at the units of the density, it's grams per milliliter. So the volume you're given is in milliliters, so you know the mass must be grams, okay? Number two, again, you are given the volume and the mass and asked for the density, right? So this time in the formula, I'm missing the density. The mass I'm given is 95. The volume is 950, and when you divide those, you get 0.1, right? So I'll write it as 0.1. Now again, how do you know the units? Well, again, the mass was on top, which was measured in grams. The volume is in milliliters, so I have grams over milliliters, so that's grams per milliliter. Okay. Number three, you're given the mass of a rectangular block of copper, and you're asked about the density, okay? Now again, we need the volume of the copper. That's not what they gave me. They gave me the dimensions of the copper. But again, if we use what we learned last week, we know the volume of a rectangular solid is length times width times height. Okay, so I can get that volume first, okay, which is 212.52. And now I have everything I need to get the density. So the density here, so again, if I were writing the units of that volume, by the way, do you see my measurements are in centimeters? So this would be centimeters cubed. Okay, so the density is the mass, which is the 1896, divided by that volume we just found. Okay, when we get that, we get 8.92. Now again, units. The top measurement was the mass in grams, so it's grams per. The bottom measurement, remember we were centimeters, so it became centimeters cubed. Okay. All right, as far as the population density ones go, okay? So number 5 gives us the area that it's in, and it gives us the population density in people per square foot. So this is a problem with people, and they want to ask us what the actual population of the people are, okay? All right, so on this one, we're going to use this formula that the population density is the population divided by the area, okay? So here I have the area, I have the population density, right? So I have 0.004 equals the population is what I'm looking for, 70,000. So again, it's just another cross multiply here, okay? And when you cross multiply on this one, you get 280. Again, the units here would just be people because the population density is in people per square foot. okay? So this will just be people, okay? Then one that's a little more challenging is number 7. Number 7 gives us 2 Petri dishes. It gives us the dimensions of each Petri dish. It gives us the number of bacteria of each Petri dish, and it asks us which one has the greater population density, okay? So population density, again, we're gonna need the population divided by the area. Okay, so for each of these, we're given the population, but do you see we don't have the area of either one of these? Okay, but it's something we can find the area of because the Petri dishes are just circles. We know the formula for area of a circle is pi r squared. Okay, so for Petri dish A, okay, so the area of A is pi. The radius here is 25.5. because again, they give us the diameter is 51. Okay, so you might just want to, it's okay to leave this in terms of pi, right? So when you square this out, you get 650.25, and let's just tack on the pi. So I've got the area of A, okay? I also need, for this problem, the area of B. So that's gonna be pi, again, half of 75, ends up being 37.5 squared. Okay, so again, if you square that out, you get 1406.25. Let's tack on the pi. Okay, so now we have the areas we need, so let's compare the population densities. Okay, so for A, the population density is going to be the population of A, which is 40,000, divided by the area of A, which is 650.25 pi. Now remember, if you want to type this all into your calculator at once, make sure you use N over D. If you want to use the divide symbol, you do have to put this 650.25 in parentheses, otherwise it's not going to divide it correctly. Okay, so here you get 19.58. Okay, so then we're going to find the population density for B. So that population is 720,000 divided by the area of that Petri dish, which we found to be 1406.25 pi. Again, using N over D is the better way to do it. You end up with 1630 is the population density. They did ask us in this problem which one has the greater population density, so that would be population A. Okay, is the one with the greater one. So even though it is a smaller dish and you think greater, you might look at this problem and think, oh, it's going to be B. It's not. So all that just means is there's more packed in bacteria in that Petri dish. Okay. All right, so that's it with densities. It's either a regular density or a population density, okay? And there's not much to it because it's just a simple fraction is the formula. So you're just going to be missing one thing in that formula, okay? All right, the second thing I want to talk about in today's lesson is rotations. Now, rotations are one of those things we start with a 2-dimensional figure, and then we end up with a 3D figure. If you remember a couple weeks ago when we talked about cross sections, we started with a 3D figure and we chopped it in such a way where we were left with a 2-dimensional figure. So it's kind of the reverse. But when you're going from 2 dimensions to 3 dimensions or backwards or forwards, it can get a little confusing because you kind of have to picture these things in your head. You don't have like the 3D model in front of you. Okay, so there's really 3 kinds of rotations, 3 things you're going to be asked to rotate. Okay, you're either going to be asked to rotate a triangle, a rectangle, or a circle. Sometimes it would just be on the regents, just a multiple choice. Like if you rotate a triangle, what 3-dimensional figure are you going to get? And what they mean by rotating is if you spin it around some sort of axle, right? An axle would be just a straight line. It's either a straight horizontal or a straight vertical, whatever it may be, okay? So in the case of the first example, so I have this right triangle. So let's start with a right triangle. So if they give you a right triangle, they're either going to ask you to rotate it around one of the legs. Okay, so in this case, if I rotate it around this leg, so I'm going to spin it. So imagine spinning it really fast. And if you've done this with anything, if you had a flag in your hand or something, Or, you know, if you start to spin it real fast, it kind of looks like it's taking 3D shape. Well, here's the thing. If you rotate this triangle very fast around this, what's going to end up happening is, and this is how you can tell what 3D shape you're going to get. If you reflect this triangle over that line, right? So that line becomes the symmetry, and then turn it into a 3D shape by just kind of circling around up from one point to a point, you can tell that you're going to get, in this case, a cone. Right? So do the same thing with this one. If we send it around the bottom leg, to figure out what we're going to get is, okay, so once again, reflect it over that point and then take 2 points, point to point, circle them out. Do you see you're also going to get a cone? That's still a cone. It's just on its side. Okay, if they ask you to do it with any other triangle that's not a right triangle, they pretty much are only going to ask you to do it. It'd be an isosceles triangle and you'd go right down the center. Okay, so isosceles or equilateral, but you go right down. So in this case, if you're rotating around the symmetry line already, so do you see what's going to happen here is this is already the line of symmetry. So this part is going to reflect on this part that's already here. So basically that triangle is going to stay in place, but it's just going to become a 3-dimensional triangle. Okay, so the theme you can see, no matter what triangle I get, when I rotate a triangle, I always get a cone. Okay. You could be asked same thing to rotate a rectangle. Again, to figure out what shape you have. So if I take my rectangle and I rotate it along one of the sides, right? In this case, the vertical side, the triangle is gonna reflect with 3 dimensions. And do you see what you're gonna end up with? A cylinder, right? If you go down the other side and reflect, and again, connect point to point, do you see you also get another cylinder? It's still a cylinder, okay? It's just going the other way. Same thing if you actually cut the rectangle in the middle, so it's already the line of symmetry, same thing with this one above. This rectangle is gonna stay put because this is just gonna spin right over the spot that was already in. Again, it's just gonna be in 3 dimensions, so you still get a cylinder. So anytime you spin a rectangle 3-dimensionally, you get a cylinder, okay? I bet you could guess what you get right now when you send a circle. Now, if you're given a circle, you're always going to be reflected. It's going to be right down the middle. They're not going to ask you a problem where it's like on the side of the circle. It's always going to be right down the middle of the circle. So if it's right down the middle, remember the figure's going to stay put because that is going to stay there. Throw in 3 dimensions and we get a sphere, right? So it wouldn't matter again if we went here to here. Again, it would go this way, but do you see you would still get a sphere no matter what. So spin a circle real fast and you end up with an image of a sphere. Okay, so the questions that ask that are on the page, the PDF page 32. Okay, so 32, what they do is they just put these shapes, these rectangles, circles, and triangles, and put them on an axis. And then if they put them on an axis, they can ask you not only what shape do you get, what's the volume of the resulting shape, which is fine because don't we know, again, recall, we already know the volume of a cone, right? So remember, volume of a cone is 1/3 pi r squared h, right? We know volume of a cylinder is just pi r squared h. And we know volume of a sphere is 4/3 pi r cubed, right? So we already have formulas for these. So we're just gonna need these 3 formulas. All it is we're just gonna have to figure out with the resulting figure, what's the radius that you get, and in the case of the cylinder and the cone, what's also gonna be the height, okay? So it's going to depend on what you're rotating over, okay? So typically we rotate either over the x-axis or the y-axis, right? So depending on what you rotate over, you could get a different, you still, again, if you are sending a rectangle, you're going to get a cylinder no matter what. But depending on which axis you send it over, the dimensions of that cylinder could be different, okay? So again, how do you figure out what the dimensions of your cylinder are going to be? So in number 1, I'm starting with this rectangle, and again, I have the units here is 3, the units here is 2. If I send it over the y-axis, it's gonna reflect this way, and my cylinder is gonna go this way, right? So that's where the circle is, Okay, so again, you could circle it in wherever you want. It wouldn't matter if you circled it here or up here. That circle would still have the same radius. Okay, so what do I know here is the radius goes from the center. The center is always going to be what you're spinning around back to the end of the cylinder. So do we see, we can clearly see here the radius is 3 units. The height is going to go from the bottom to the top of that cylinder, okay, which was just the height of the original rectangle, which we see here is 4, okay? That's all I need because volume is pi r squared times height. I'm just going to leave it in terms of pi here, and we get 36 pi. Okay, had we rotated over a different line, we would still get a cylinder. It would just be a different size cylinder, okay? All right, so number 2, same thing with number 2. We have a triangle, we know we're getting a cone, right? We automatically know we're getting a cone, so we're dealing with 1/3 pi r squared h, right? Any triangle is gonna make a cone. Again, it depends on what you're rotating over. This time they told us to send it over the x-axis. So if we wanna see what the cone looks like, we're gonna reflect this triangle, right? And then we're just gonna kind of spin it out. We're gonna put in the circular bottom. Okay, so we have a sideways cone. Okay, so what do we need to know about this cone? Well, we need to know the radius. Remember, the radius is from the center down to the end of the cone. It doesn't matter which way you count. You could count down or up. Either way, you're gonna get 3 units on this one, right? The radius is 3. Okay, so again, it's that height of the original, it's the leg of the original triangle. And then the height of the cylinder goes from the circle to the tip of the cone, So in this case, that one was 1, 2, 3, 4, 5. Okay, so that was again. So the radius and the height of the cone end up being the original sizes. It's one of the sides and the other side. But do you see, we just have to have it right because we'll get something different. If we had sent it around the other axis, the only difference really is these would change. The radius would now be 5 and the height would be 3. So it does change the volume, right? So this is 3 squared times 5. So if you do out this math, you get 15. Let's tack on the pi and leave it in that form, okay? So again, you just have to make sure you kind of draw it so that you can identify the radius and the height. That's it. It doesn't have to be a great drawing, just enough so you can do that, okay? Number 3, I am starting with a circle. I know I'm gonna get a sphere. So I know I'm dealing with 4/3 pi r cubed. For a sphere, I only need to know the radius, right? So it's kind of simple. The radius of the sphere, I'll tell you right now, is going to be the same radius of the circle you started with. Because remember, you're going to be sending it, spinning it around the middle of the circle, so it's all just going to stay put. So this is just going to go to 3D, but the radius is still the same radius as the circle, which in this problem was 3. So if I plug 3 in, okay, here I get 36, and I'm going to just tack on my pi. Okay. Then this final problem, okay, so this is one of those, I've got another one that kind of stays put. So again, I'm starting with a triangle, so I know I'm ending with a cone. So remember, for cone, I need to know the radius and the height. The good thing about these ones, again, remember when you're sending it right down the center of either a triangle or a rectangle, everything is going to stay put. This is just going to go to 3D. So what you're going to end up with is a radius, right? Goes from the center to the end of the triangle, which again, if we count boxes on this problem, it ended up being 3. Okay, you could clearly see it on the graph in that problem because everything was gridded off. Okay, and then the height is just from the bottom of the triangle to the tip of the triangle, which in this case was 7. So pop it into the formula and we are done. Okay, so here we get 21 pi. There's no units on any of these problems, guys, because we're on a grid, so they're not giving centimeters, inches, or anything like that. Okay? All right, so that is it for this week. Okay, that's where we're going to stop for this week. Okay?